Was it? I hope so. Tell me that, because it makes me feel like this time spent is worth it. So today we're going to dive right in and start getting into the main meat of some of the definitions and try to get some intuition. So last time, remember what we did is we talked about information, communication, and when we're communicating, we're essentially somehow imparting information from one place to another, or from one time to another. But then we talked a little bit about what information was, and we acknowledged that maybe we are not going to have a complete sort of, at least intuitive definition of information. We're going to have a very utilitarian definition of information. And our definition of information is going to be based on entropy, which we only mentioned but we didn't define. The one thing we did sort of tend to agree on was that if we actually are basing it on the probability of events, like if the world is random and if the events are governed by a probability distribution, then when things are improbable, we tend to sort of believe that those are more informative than when things are probable. Probable things are less informative than improbable things. And the reason is because if we know the distribution and there's something with probability 1 and it happens, then we're not surprised at all. And entropy is going to be our mathematical characterization of information, even if it doesn't capture all of these other aspects of information, like we saw the semantic things like the painting and the poem. So once again, this is the wrong book, and I guess I didn't fix this typo. But anyway, read chapter 1 in Cover and Thomas, chapter 1 and 2, and read, including Fanner's inequality. So try to read all of that stuff before class. Has everybody got the book? And has everybody started reading? Okay, good. So if you've read chapters 1 and 2, then this lecture will be very familiar to you. And homework 2, as a reminder, is due this evening. Sorry, homework 2. What happens when you're frustrated by the laptop. So homework 0 is due this evening. It's not created, but it counts credit, no credit. And then homework 1 is posted. It's actually there now. And again, you turn it in. This is our place. This is where we turn in all PDFs. And please, one other thing I wanted to ask you. So I've been sending announcements. I haven't been sending out that many emails, but I've been sending announcements on this Canvas thing. So Canvas is is the first time I've used it. And has everybody been able to is everyone getting the emails when I post announcements? Yes. I read an article that students don't use email anymore. I'm not sure. Maybe I should be posting on Facebook and Twitter. But you guys are graduate students, so maybe I don't need to do that. But raise your hand if you did not get the announcements that I posted on Canvas by email. So when I posted an announcement on Canvas, raise your hand if you did get an email notification when I posted the announcement on Canvas. So you didn't?
I'm auditing the course, so numbers.
Are you an official audit?
Officially,
As part of the registration process? I mean, are you in the books as being an auditor, or are you just sitting in?
No, I haven't.
You're not sitting in. Okay, so, well, if you'd like to officially audit, that would be great. It actually means that there's more interest in the course, and I usually encourage people to officially audit. It doesn't actually do anything. It just means that there's somebody sitting in the class. However, if for some reason you don't want to do that, I'm also okay with that. And if you would like to get the announcements, send me email, and then I can actually add you, even if you're not an official auditor. This thing apparently has the ability to do that, which I've discovered recently, but I don't know if it works. Maybe it works. Okay, so any questions? So we're going to dive right in, like I said. So entropy. So entropy is something that's going to be pretty much our measure of information for the coder. Let's say that we have a set of events. E, K is an event, and an event occurs with some probability p sub k. So and the Shannon information, the information about this event is log of 1 over the probability. So just right away, I'm just going to give you this piece of information, which is the definition of our information of an individual event. So first of all, let's just look at this for a second. This sort of satisfies our intuitive notion of what probable and improbable events mean in terms of the information that we get. Like if there's a certain event, if the probability of pk is 1, then we get 0 information. And if pk is 0, we get infinite amounts of information, right? So that's the information about an individual event. So there's a number of ways of actually interpreting this. You can actually sort of think of it as a measure of the surprise of finding out ek. So if it's probability 1, then there's no surprise, whereas probability 0 gives us infinite surprise. It also gives you, in some sense, the amount of information, like what we've been using. It's how much new stuff have we learned when we find out that EK has occurred. So it's like surprise, or you can think of it as information. You can also think of it in some sense as really sort of the uncertainty, or maybe a better word is the unexpectedness of the given event. The notion of uncertainty is something that's going to come into play in a little bit while later. So let's really think of it as unexpectedness. And so then this thing here, the I of EK, the information of EK, is really sort of like the self-information of the event. Now, what do we mean by self-information? We will see that very soon, because we will be talking about things of self-information. So by the way, so all bases, when we talk about this log, all bases by default in this class are going to be log base 2. So you can also think of this as being measured in bits. But on the other hand, we could also use other bases as well. They're all equivalent, of course, up to a multiplicative constant. So now the word uncertainty, like I said, doesn't really apply to the individual events, because it's not like how uncertain are we? I mean, uncertainty says we don't know which of amongst a number of different things might happen, right? It's either this, or it's either that, or it's either that, and I'm not sure which it is. It's really the unexpectedness is something that sort of measures the information or the individual event measure. Like, for example, if the probability is equal to 0 of x, we are certain about it not happening, and we're certain about x happening when the probability is equal to 1. So uncertainty sort of corresponds to both 0 probability and 1 probability. Right? So maybe that I of E doesn't really correspond to the notion of uncertainty. So that's why we say that sort of surprise or unexpectedness or some of these other words, if you're interested in the intuition, are better words for describing I of E of x. Okay? So unexpectedness, that's really the key. Oops, I don't want to cross that out, so I want to highlight it. Okay. So entropy is actually the word that we're going to be using to sort of measure the information of a collection of events. Now, first of all, where does the word entropy come from? Shannon actually coined or used the word entropy, but it was based on Rudolf Clausius, who was a physicist in the 1800s, who basically coined the term entropy to correspond to sort of a combination of trope, which is really a Greek word for transformation, and N, which is like the En in energy. So it's like entropy, which is like energy transformation. And the reason why entropy corresponds to energy transformation is because it's sort of like the degree to which energy has the potential for transforming from one state to another state. So it's like the transformation of energy. That actually, if some of you have taken statistical thermodynamics or physics, that corresponds to the notion of entropy that we see in statistical mechanics. Right? But then Shannon used the term entropy as well, and we'll see why in a minute. So just for a set of notations, just in case this isn't clear. So when we talk about P of x, this is really the probability of an event. It's the probability of a random variable taking a particular outcome. And we're going to use a lowercase variable to correspond to the outcome. What this really means is the following. It's the probability distribution under for that particular random variable x. So that means that we're indexing a probability distribution of the random variable x equaling that particular value, which is the event. So the event, if you think about the probabilistic event, it's really capital X is equal to lowercase x. So in this class, pretty much uppercase letters are going to correspond to random variables. Lowercase variables are going to correspond to outcomes or possible values of that random variable. And then as a shorthand, we're just going to use this notation. And it should be clear because we're not really mentioning the random variable here, nor are we mentioning the actual name of the distribution. It's implicit. There's no subscript here. But that should be very, very clear. And if that's clear, if that's not clear to you, then it needs to be. Okay, because otherwise you won't understand anything else. So given a random variable x, we can compute the expected value, and that basically just sums over all values of x here, and multiplies it by its probability. It's like the average, and if it's a uniform distribution, it's exactly the average, right? And given a function of a random variable, g, we can compute the expected value of that function of the random variable. In some sense, g of capital X becomes a new random variable. It's a transformation of the random variable, and we can compute its expected value in the same exact way. Okay. Now, suppose we take g of x is equal to log of 1 over p of x. Okay. So g of x is just some function that just happens to be equal to the log of 1 of the probability of that particular random variable. Okay, so it's just any function. And we can actually then take the expected value of that function. So just like what we did here, where we took the expected value of this function of a random variable, we can do the same thing here. But here what we get is this quantity on the right. And this quantity on the right is going to be our definition of entropy. It's the entropy of the random variable x. And what it really is that it's the expected surprise, or it's the expected information, or the expected unexpectedness, the expected that using the other term. So it's a little bit funny in this way because you're sort of using the probability twice, but the probability, let's sort of zoom in a little bit on this. This is the thing, this is the probability that's giving us the weighting, right? This is doing how important it is, and this is the value, right? So remember, when something's very, very improbable, it has a lot of information. So this part, the log 1 over p, is big, but this part is small. On the other hand, when something's very, very probable, so it doesn't have a lot of, it has a lot of expectedness, we're expecting it, this part is going to be big, it's going to be close to 0, and this part, well, I should say small in absolute value, it's going to be close to 0, this part's going to be big, it's going to be close to 1. And then we add them all together, where it's like the expected surprise, or the expected unexpectedness. So here's the expected unexpectedness. And it's also the definition of entropy. So here's the definition, the formal definition. So the entropy of x, which we're always going to be writing in this way, it's h of x, is the expected value of 1 over log px. Now this is an important notation here, so I'm going to zoom in on this. This is the expected value of this quantity, in parentheses. And the quantity is a random variable, right? Because what is in here is a random variable. This is random, right? And we're just taking a function of a random variable. So that quantity, it's a random function, right? Because it's something that every time we look at it, every time we measure it, it takes a different value. And so when you compute the expected value, you can do that. So there's always, whenever you have an expected value sign, there is some implicit random variable somewhere. That's equal to this, which is this definition, which we saw. And then typically, because of the properties of the logarithm, you can just write it this way, where the negative is outside. Yeah?
But for a given distribution, p of x is fixed, right?
And p of x is fixed.
So what is the randomness here? Why are we taking expectation?
Well, so this is where I mean by self-referential. So we're taking so what is this going back? So I just sort of went over this last slide. So this is the expected value of this function g, right? G of x. So it's the expected value of a function of a random variable. Let's just set g to be equal to 1 over p of x.
Yeah, I understand, but actually it's fixed, right? For a given.
That doesn't mean that the distribution is not fixed. The distribution is still fixed, but the question is it's a random variable. So whenever you have a function, whenever I write, let me write it this way. Whenever I say e of g of capital X, the random variable is capital X, and what that means is the sum over x, lowercase x now, we're summing over all possible values, sum over lowercase x of p of x, g of x, right? That's what that means. And so x is the thing that imparts the randomness inside of the expected value. And so that way we can write it in this form as well, this form here. Okay? You may need to think about this. The reason why we're doing all these different things is because there is this sort of weird self-referential thing. Because the thing it's the expected value sometimes people write the expected value in this way. So like the expected value with respect to p of the quantity log 1 of p capital X. It's another way of writing it. So you're saying which distribution. So the fact that this distribution and this distribution is the same doesn't matter. In one case it's giving you a value of a function. In another case it's the thing that's giving you the randomness. It's giving you the probability distribution. There's nothing that says you can't define a function that's random where the random value that gives you that particular value of the function also has to do with how likely that particular value is. And if that doesn't make sense, it's on YouTube and you can listen to it again and you can rewind it and hear it 10 times and say, oh, I see what he's saying. So, but that's true. Okay. So entropy is going to be in units of bits, since log's a base 2. Sometimes people use nats, which are log base e, but that's not so important again because it's identical up to a multiplicative constant, meaning it has nothing to do with the probabilities. It's just a multiplicative constant because you can convert from one log to the other. So this now, entropy really does measure our degree of uncertainty, as we will see. Unlike log of 1 over p of lowercase x, which is really sort of the unexpectedness of an event, this actually is the uncertainty because it's going to essentially correspond to, it's going to have different values depending on how certain you are that one thing is going to happen or how uncertain you are about how many different possible things is going to happen. And so this, by the way, if this doesn't make sense yet, it will soon because we're going to actually start looking at this. So this also measures the disorder or the spread of a distribution. Just like entropy in statistical thermodynamics, it also corresponds to the disorder. It also measures, in some sense, the choice. Like when you have a uniform random distribution, you have a lot of choice. Like that random distribution can in some sense, pick and choose uniformly. And as long as it's overall uniform over all symbols, it has lots of choice. When you have the opposite, which is a deterministic random variable, where only one value has value 1, has probability 1, you have no choice. You have to keep choosing, every sample has to keep choosing that thing. Like imagine a fair coin. Keep flipping a fair coin, you have about equal choice between heads and tails. Now imagine a very, very, very biased one-sided coin. Can you build a one-sided coin? But imagine you built a one-sided coin, or something, a coin that has probability 0 of being heads and probability 1 of being tails. That coin has no choice. And we can actually look at the distribution. So here's a distribution. Let's say that the horizontal axis is the different possible values of x, and the vertical axis corresponds to how likely that particular value is, or the probability. You can think of this as a histogram. So do you think this is a relatively low entropy distribution or high entropy distribution?
Low.
It's probably a low entropy distribution because it's fairly concentrated. There's not a lot of choice. What about this one? It's closer to uniform. It's not exactly uniform, but it's closer to uniform. This is probably more high entropy. And then this one maybe is somewhere in between. Right? So low entropy generally corresponds to very concentrated probability distributions. High entropy corresponds to very uniform distributions. So therefore, it sort of measures like the average uncertainty, which is a measure of the entire distribution. When it's high entropy, it means you have a lot of choice. There's a lot of uncertainty. You have no idea what's going to happen. Well, it could be this, it could be that, it could be that. I don't know. No clue. On the other hand, with the low entropy distributions, and well, I'm pretty sure it's going to be these values here. I would place my money if you were betting. Does anyone gamble? If you were blackjack, I mean, it wouldn't be great if all the distributions were low entropy. Well, actually, everybody would win. That wouldn't be great if you knew it was low entropy in a particular way. But if you were gambling, you'd say, I'm going to place my money in that yellow region. I'm going to bet that outcome, not the other outcome. And you would probably do pretty well. You'd win. Whereas in this low entropy in this high entropy distribution, this uniform distribution, you would have no chance of winning because you'd never be able to predict what's going to happen with any level of confidence or certainty. So entropy, this is an important point, it's a measure of the entire distribution. It's the whole distribution is used to compute the entropy. It's the sum over x, p of x log of 1 over p of x. Right? So you need the whole distribution. It's not just a value, it's not just a function of one probability. Entropy measures the expected degree of uncertainty of the outcome of a probability distribution. It's an expected value. And also it measures the disorder or spread. High distributions are flat, more uniform, although entropy distributions should be, I'm not sure that's a proper technical term for this, but few modal, it sort of like means it doesn't have a lot of modes, like maybe one concentrated mode. Let's measure choice. Okay, let's do some examples, some very simple examples. Let's start off with a binary random variable, like a coin flip. Let's say that 0 is tails and 1 is heads. 0, 1 outcome random variable. Let's say that the probability of 1 is p, lowercase p, which is 1 minus the probability of 0, so it sends to sum to 1. So the entropy of this distribution is just the following. We can write it as this, right? So it's h of x, which is just our general notion of entropy. So it's, remember, it's the sum over x p log 1 over p. So we can just, let's just not deal with ratios and stick the minuses outside. So it's minus p log p minus 1 minus p log 1 minus p. Okay. Which we often write it as this. We often write it as h of p. Okay. So because where p is the probability of a single outcome. Because the other one, probability of 0, is already known. So when we actually look at it as a function of p, so lowercase p ranges from 0 to 1, 0 over here to 1 over here. We see that the entropy starts off at 0, like the entropy, let's zoom in on this a little bit. Entropy starts off here at 0. As we increase the probability to 0.5, it maxes out at 0.5, which is what we'd expect because a uniform, a fair coin, is one that we can least well predict. It's least predictable, it's most uncertain. We have maximum entropy for a uniform distribution. And then when the probability starts going up to 1 again, the certainty starts increasing, the uncertainty starts decreasing, and when we get to 1 again, the probability of 1, we're certain about it again. And by the way, this is the actual plot in MATLAB of what the entropy looks like. So it's not a coincidence that it happens to be concave. We will talk about concavity properties of the entropy very soon. But in general, the entropy, as we expect, is maximized when the probability distribution is 0.5, or uniform, and minimized when it's deterministic, when it's 0 or 1 in this case. Any questions about this? Yeah, it's concave. We already talked about that. So, any questions? We're going to generalize right away. We're going to generalize to the entropy of 2 random variables. So, there's nothing special about 2 random variables together in a joint distribution. It just so happens to take values in a grid rather than along a line, say. So, they can be related. They don't have to be independent. So, we have 2 random variables, x and y. And the joint entropy of the distribution x and y is, as you'd expect, we just sum over all the values of x and y here and take the expected value of the log of the probability of that particular value of x and y. And again, we stuck the negative side outside. And then we can write it in this way. Actually, what I said, so if I were to write this according to what I did before, these guys should be capital letters x and y. Right? So that's where the randomness comes from. Any questions? Okay. Why not generalize to more than 2 random variables? Well, we can certainly do that as well. The entropy of a vector of n random variables is just written as the sum over all possible values of that vector. The probability of that vector, and then the log of 1 over the probability of that vector. So that's the vectorized entropy function. This is something that is, you can easily write it down in this way, but if for example, if you wanted to try to compute it, it would be hard because let's say even that the x's are binary valued, so that each x has a value of 0 or 1. There's going to be an exponential number of terms in this sum here, there's going to be an exponential number of those things. And in fact, if it's binary, it's going to be 2 to the n. So as n gets big, as the number of random variables gets big, you're going to have to sum over 2 to the n terms. And when n is 1,000, forget it, right? N is even 50. I mean, it gets very, very big very quickly. Okay, conditional entropy. Any questions about joint entropy? Is that pretty straightforward and clear? Raise your hand if you've seen this before. Okay, raise your hand if you've never seen it before. Okay, raise your hand if you understand everything. Raise your hand if you're confused at 20% confused. Okay, good. I think we're in track. So conditional entropy. So we can talk about entropy, but also conditional entropy. So what does that mean, first of all? So we have 2 random variables, and they're related by this joint probability distribution, P of x and y. Okay. Now, let's say we're interested in just in the entropy of y. There's 2 ways that we might be interested in the entropy of y. In one case, you might say, well, what's just the entropy of y? And we'd sum over y of p of y log 1 over p of y. Right, this is the entropy. But what if these things are related? You say, well, I know that x happened. I know that x had value lowercase x. Right? So what that means is that the distribution of y becomes probability of y given x is equal to x. Right? Lowercase x happened. And now I've got a new distribution on y, which could be very different than the original distribution. Right? And so we want to know the entropy of this new distribution on y. So the way we do that is define something called the event conditional entropy. Let's zoom in so you can see. Can everybody see the board? I know I really hate, we have such great windows, and I hate closing the blinds to block the sun. I personally love having light, natural daylight in a room. It's a luxury. So I prefer not to close them. But on the other hand, it's important that everybody see the screen as well. So can everybody see the screen? I'm trying to do the zoom thing. So that people can see better when we're talking about this. But let me know if you're having trouble seeing it, and maybe we can put out some sheets or something. I don't know. Anyway, so this is conditional entropy. So the event cap x is equal to lowercase x. And then we look at the distribution of y. So it's got a very sort of natural sort of definition, because it's saying, well, we're summing over that distribution y under the event that x is equal to x occurred. And otherwise, it's the same definition of entropy. Right? But now, suppose we were interested in, saying, well, what's the average over all x's? But we can take, this is something, this is just a value. This whole thing is not a random quantity. This is just a value. We can take, and it's a value, this is really a function of x. This is a function, f of x. And we could take the expected value of this function of capital X, right? And that's going to give us the actual conditional entropy, which we get here. So here's that function of x. Let's zoom in a little bit again. Here's the function of x here. Right? This is really f of x. And then we're just taking the expected value of it. And then when we expand everything out, we just get this. Get this guy, or this guy, or this guy. And notice in this bottom one, which is sort of interesting, this one down here, we have two random variables, x and y. Right? And we just take the expected value with respect to both of them, which basically means what we're doing is we're really summing over this quantity, which is a function of x and y, times the probability of x and y. So this is sort of like what we did before. It's kind of like where we have like g of x and y is equal to log 1 over p of y given x. And then we're just taking the sum over x and y, p of x and y, g of x and y. It's just a different definition of g. It's based on the conditional probability. Questions? Okay, our first proposition is that we've got a notion of chain rule. So the joint entropy, this is very important. We're going to talk about properties of entropy. So the joint entropy, x and y, is equal to the singleton entropy plus the conditional entropy. And by symmetry, it's equal to this singleton entropy of h of y plus h of x given y. So what does this mean? The uncertainty in the joint set of random variables x and y is equal to the uncertainty in x plus the residual uncertainty in y knowing x on average. Right? So we have an additivity property. Equivalently, we can say the uncertainty of x and y together is equal to the uncertainty of y plus the residual uncertainty of x given y. So this is like the residual uncertainty. This is like the uncertainty that's left over. Because in some sense, when you know y, y tells you about something about x. Maybe it makes it higher entropy, maybe it makes it lower entropy, but on average, it tells you something about x. On average, and if these things are correlated, it tells you something. If these things are independent, it doesn't tell you anything. But it's got to tell you something. And so the idea, what this kind of means is that in this particular way, that you can sort of decompose entropy into parts consisting of, uncertainty and residual uncertainty. And the way to prove this is very simple. We just use the chain rule of probability in equation 2.12 and get the result, thanks to the linearity of the expected value. Another corollary is that if x is independent of y, so this symbol, by the way, everyone should be familiar with this. It means that x and y are independent. If these are independent, then the uncertainty about x and y is additive, strictly additive. There's no conditioning involved. And essentially what this means is that if x and y are independent, the uncertainty about y given x is equal to the uncertainty about y. I'll mention that again, but I guess the immediate corollary is the independence. And the reason for that, of course, is because, again, you go back to equation 2.12, and p of y given x is just equal to p of y, since it's independent. Everybody good? Okay. There's a chain rule for entropy, just like there is the chain rule for probability. So we choose an ordering of the random variables. This is true for any ordering. I've done it for a particular ordering, which happens to be the ordering that the random variables are indexed by. But the ordering doesn't really matter. So the ordering is such that, we've got the joint entropy of n random variables is equal to the entropy of the first one plus the entropy of the second given the first plus the entropy of the third given the first two plus the entropy of the fourth given the first three, and so on and so forth. All adding together. I think I've got some examples here. Maybe I don't. Let me just write it in case that's not clear. So the entropy of x1 through xn is equal to the entropy of the first one plus the entropy of the second one given the first one plus the entropy of the third one given the first two. And I hope the pattern is becoming clear. The entropy of the fourth one given the first three, and so on. So entropy is conditionally additive. To prove it, it's the same thing. We just use the chain rule of probability, which holds, again, for any ordering, not just the index ordering. Use the chain rule of probability, take the log and the expected value. Logs of products turns into sums, and thanks to the linearity, we get the result. Everybody with me? Okay.
Did you write h of x1 plus h of x1 given x2?
In here?
Yes.
Yeah.
So aren't you missing a term that?
Sorry, I'm not sure where. So the first one is h of x1. So when I is equal to 1, there is no I0. So this underlying assumption is that when I is equal, x of I is equal, when I is equal to 1, it goes 1 through 0.
Yeah,
It cancels out, yeah. Yeah, this is, by the way, this is a good question. So if this isn't clear, you see this all the time. So when I is equal to 1, that implies that this whole thing is equal to the empty set. because it's in increasing order. You're starting at 1 up to I minus 1. You can't increase order from I to 0. That's not an increasing order, so therefore it doesn't exist. And also x sub 0 doesn't exist. So just by definition, that's defined as the empty set. And that's universal. I see that everywhere. You should be familiar with that. Notational. It's a notational shortcut. And in fact, any math notation is a notational shortcut. All of math is a notational shortcut. We could do everything with long handwritten English if we wanted to. For example, I could say h of x1, comma x2, comma so on and so forth is equal to the sum for I is equal to 1 to n of the quantity h of blah, blah, blah. I could say all this stuff out in a long sentence, and basically one equation would be the entire lecture, or at least with all of these slides. I don't want to do that. We have math because it's a shorthand, it's a shortcut. And we agree upon what it means so that we can efficiently communicate complex ideas very precisely. That's why we use math notation. Convex analysis. Okay, so let's talk a little bit about a variational representation of a particular function. So let's look at the natural logarithm of x has a variational expression, and it's equal to the min over lambda of lambda x plus ln lambda minus 1. To show that that's true, by the way, it's very simple. You just solve, you take the derivative set equal to 0, find lambda, and you plug it in, what you get is x. So it's an identity. But what it means, however, is that we can come up with sort of a variational upper bound on the natural logarithm in terms of equation 2.17. So for any value of a lambda, this is an upper bound of the logarithm. This might be useful because it's linear in x, right? Suddenly we've upper bounded a logarithm with a linear function. We have a free parameter, a variational parameter, which is lambda, which we can vary. That's why it's called variational, I think. But we have lambda is equal to 1 is a particular upper bound, and we get this upper bound, 2.18, which you've probably seen before, right? Natural log of x is upper bound by 1 over x. I mean, there's many instances of plots where you see this, right? So with that upper bound, natural log of x is less than equal to x minus 1, let's prove that the entropy of x is no greater than log of n, where n is the number of outcomes. So we have a random variable x which has n possible outcomes. It's not n random variables, it's n outcomes, n possible values of the random variable. These are discrete random variables. The maximum entropy, which occurs, we know, at least we've said, occurs when it's uniform. The value when it's a uniform distribution is log of the number of entries. And equality is achieved at the uniform distribution, which I guess now we're going to actually prove. The first thing we're going to do is show that the entropy minus log of n is less than 0, which shows that it's an upper bound. Then log n is an upper bound. Then we have to show an achieving distribution. Actually, the achieving distribution part is really easy. You just sort of plug it in and you get log n. All we need to do really is show this upper bound. So the way we do this is h of x minus log of n. Let's just write it down. And the log of n, we're going to take the expected value of a log of n, which is redundant because the sum over x is equal to 1. Sum of x of p of x is equal to 1. So this bit here is the same. This bit here is the same as negative log n. Let's change the base of our logarithm by multiplying by a constant, log base 2 of e. And then we get this quantity. The expected value, according to x, p of x of the natural logarithm now of 1 of p of x times 1 over n, right? Or 1 over the quantity p of x times n. And now we use our variational bound. So basically what we are doing is here, we're saying log of this quantity is less than or equal to that quantity minus 1, which is down here. Okay. But now we sort of combine stuff together, cancel things out, and we get log of 1 over n, because the p of x cancels out, minus this thing, which is the sum. But this right now corresponds to 1, right? And the first thing is just 1 minus 1, which is 0. So this becomes 1 minus 1, so this whole thing is 0. So it's basically log of e, which is just constant times 0, which proves the inequality. Okay. And like I said, we can achieve tightness in the inequality by essentially using the uniform distribution, which gets the value. So basically we have an upper bound on something and something that achieves it. Now, no questions? So we will be proving some theorems in this class, by the way. Some are easier than others. This is maybe a little bit easier of it. So now we have, I guess here's another way. This is the uniform case. So we have, when z is equal to 1, the above becomes inequality. So when this quantity here, this bit here, let me just see if I can get this thing. That's good. This bit here is equal to 1. Okay. And that happens when p of x is equal to the uniform distribution. I mean, another way of doing it is just sort of plug in the uniform distribution. So the uniform distribution, you get the negative the sum of 1 over n of log of 1 over n, right? So the negative sign outside becomes log of n, and then the log of n is a constant. You bring that out, and it's the sum over x of 1 over n, which is n times 1 over n, which is 1. So we've got log of n. So you achieved an upper bound. So this stuff doesn't even matter. Or at least that's a little bit more complicated even than you need. In fact, what I just said was what I wrote here. So I guess I prefer this way. What I'm saying is, that's what I just said. And we'll just pause for 1 second so you can chew and digest this equation, and then I will move on. Okay. Now, it turns out that the uniform distribution is the only distribution that has that property. If you change the distribution even slightly by going from the uniform distribution, adding a bit to one and removing the bits from the other, it's basically the notion of it's strictly concave at the maximum point. So any budge will decrease the entropy slightly. So the uniform distribution is the true maximum entropy distribution. So what this means then is that if distributions become more uniform, as things become more uniform, the entropy is going to increase. Uniformity, which we sort of intuitively said corresponds to maximum uncertainty, is maximum entropy, and degrees of uniformity, as you're more uniform, you're more uncertain. Like one way of increasing uniformity is by mixing. If you take a mixed distribution, that's going to have entropy greater than the average of the entropies beforehand. And this is a property of the concavity, which we're going to show very soon. But basically, it's saying that if you look at the average entropies, I mean, the entropy of the average is greater than the entropy of the average of the entropies. So mixing sort of, on average, increases the entropy. Okay, what are some other things that might increase the entropy? Like, let's say that x is a random variable indicating a positions of cards. So the idea is like each x is a permutation of the cards. Or I should say permutation. So each outcome of the random variable is an ordering of all 52 cards. And let's say that T is an operation that takes, in ordering, whatever it happens to be, and shuffles it uniformly at random. So basically, it takes the cards, takes them, reorders them uniformly at random. Permutation operation. And we can show that the entropy of the shuffled deck is greater than of a shuffled version of x is greater. So now, the question is, what does this mean? Remember, x is a random variable over permutations. There's a distribution over all possible permutations. X does not necessarily mean that we have equal probability of all permutations. If you go gambling in a casino, maybe there's a very non-uniform probability of a particular distribution. But the point is that X has some distribution, and then if we shuffle it, and now we look at the distribution of the shuffled deck, that can only increase the entropy, can never decrease it. Now, it could be that h of x is already maximized out, in which case this wouldn't do anything. But remember, it's a non-strict inequality. It can only get bigger, it can never get smaller. It could stay the same. So the inequality is important here. And to show that, we can do the following. Actually, we're going to use a couple of things that we'll learn soon, but if we condition on the shuffle, that decreases the entropy. So if we already know the random variable, then this is going to decrease from relative to this. We know the shuffle. It turns out that once we essentially know the shuffle, whether or not we use it once or twice doesn't actually change the entropy. And then this is h of x given t, because this is the inverse shuffle of this shuffle. This gives us the entropy of x. And then since we assume that the shuffle and the deck, the shuffling operator and the original deck operator are independent, that's just equal to h of x. So therefore, shuffling can only increase entropies. What about permuting the probabilities? What if we take, so that was an instance where, the reason why, by the way, if you're wondering why we use something that we're going to be defining in a few lectures, is because I wanted to talk about permutations in general. And this is an important property of the entropy. So remember, the entropy is the sum over x, p of x log 1 over p of x. And now what if we permute the probabilities, as opposed to permuting the actual meaning of the outcomes of the random variables? Does that change the entropy if we permute the probabilities? No. So if we have a coin, as an example, that's 0.3 heads and 0.7 tails. If we permute the probabilities, so it's now 0.7 heads and 0.3 tails, does that change the entropy? No. So the entropy is really only a distribution, it's really only a function on the probabilities. It doesn't matter what the outcomes of those events are. So you could actually have completely different types of random variables. One could be distribution of the price of gasoline, the other could be a probability of government shutdowns. If they're the same probability, I don't know, maybe, I don't know, that's unlikely, but suppose they are, then they would have the same entropy.
I have a question about the shuffle operation. I mean, what does it actually do? I mean, does it...
Which shuffle? The probability shuffle? Or
yes. Well, not the probability shuffle, the shuffle on the permutations. So does it...
You mean the shuffle of the card deck?
Yes, but
okay.
What does it do to the probability distribution? Does it seems to kind of flatten it out. I guess you take the expectation or each point that... so this becomes like a convolution. Okay,
I'm not sure it's really a convolution, because basically here's the way you think of it. You have all n factorial possible permutations, right? And you have a probability associated with that. And you're measuring this, so it's n factorial probability values. And you start out with a distribution on x, which assigns a probability for every single possible permutation. So the next thing you do is you say, okay, now I've got a random variable, I've got a generator. Think of it as a data flow thing. You've got some random source, and every time you get a reading from that random source, it gets you an ordering of the deck with that probability. So now you have got another black box. What it does is it takes this and it shuffles things, and now you have a new ordering. Okay, so now you've got this post-processed ordering by this shuffle operator. The shuffle operator is independent with respect to the original distribution. And now you could count, like how many times is it this permutation, how many times is it that permutation. And you could estimate, say, the distribution, or you could just compute the probability. So that's what that means. And then the question was, well, like, what does it actually do? It actually does something pretty sophisticated to the distribution, but what's cool about this set of things that we just defined is that we can actually prove that shuffling increases entropy without even going and looking at what it does to the probability distribution. And what we're going to see is that the entropic quantities, we can actually learn something very fundamental about probability distributions without actually having to go through and do a complicated set of algebra to sort of figure out precisely what it does to the distributions.
But what if the shuffle operation itself is biased towards one permutation? Wouldn't that Does that increase the entropy?
Well, let's go back to the equation. So it's an independent shuffle distribution. So if it's independent, then it won't.
Because
Okay, so I mean, because you're,
yes.
it's a shuffle thing, right? It doesn't. Remember, it's a permutation of an object.
I understand.
It's not saying order it this particular way. It's saying change the order, and it's relative to the initial order. And if it's a deterministic random variable, as you just said, if it always says make 5 go to number 1, make 7 go to number 2, make 8 go to number 3, make so on and so forth. If it always does the same thing, the entry is going to stay the same because the probabilities have been shuffled, but not the actual values of the probabilities have changed. So if t is deterministic, the entropy will stay the same. That makes sense?
Yes.
It's a good question. But here what we're doing is we are permuting the distribution, the probability distribution. So basically we have a random permutation, sigma 1 through sigma n, and we're permuting the probabilities. And that's what we mean by permuted distribution. And whether or not we compute h of p, which is this, and compare it with h of p sigma. I mean, it's the same quantity. I mean, the thing is because sums are immune. At least if you don't using finite precision floating point arithmetic, sums are immune to permutations. So therefore, this is the same as that. All right. For our YouTube listeners, I need to write this down. This is the same as that. So I have to I'm lecturing not only to you now, but I'm lecturing to you Saturday evening at 10 p.m. when you're going to watch this again. Right? So everyone's going to be seeing this again. On your iPhones or Android phones. Okay, so let's do a summary so far of what we've got, and then after that we'll take a break. So we've defined the entropy of X, which is the expected information, which is defined in this way. We've got the joint entropy over two random variables, the conditional entropy. We've got the chain rule of entropy, and we've got the bound on entropy. Right? Entropy is going to be no less than 0, and entropy is going to be no greater than log n. It's going to be somewhere in between. Why is it no less than 0? Didn't really prove that.
Minus log of px is always greater than 0.
That's right. Minus log of p of x is always greater than or equal to 0, and the probabilities themselves are always greater than 0. Can it ever equal 0? Can entropy ever equal 0? We just need to find a distribution where it's equal to 0. What about the deterministic distribution where it's always one guy? So it's going to be 1 times log of 1, which is 0. And the other one's going to be 0 times log of 0. 0 log 0 is not really defined, but if you take the limit, where you can use L'Hopital's rule, you take the limit as p goes to 0 of p log p, and that's equal to 0. So it's greater than or equal to 0. I think that's good for now. Let's take any questions. Okay, so funny, the question during the break was just asked about why are we interested in the log function. Well, that actually turns out to be the very next slide. So we actually define the information using the log, right? So I mean, whereas we have this intuitive notion of well, high probability needs to be low information, low probability events give us high information. The log is one way of doing it, but there are lots of other monotone functions that could do that. For example, like the negative nth root, like the square, even the square root would sort of kind of do it. Where we take 1 over the square root would be reasonable, maybe. I mean, it would certainly give us the same kind of thing. Another example would be the number of prime factors in the seal of 1 over p, which we could use as an information factor or information function, and then take the expected value of the number of prime factors. The log function we'll see has a number of attractions. That doesn't mean that it's the end-all, be-all of information functions. In fact, information functions are a research topic in and of themselves. There are quantities called things like the Renyi entropy, which maybe I'll mention briefly in the next lecture. But critically, the log function has certain properties that are unbelievably powerful, as we will see. For example, here's one of the properties. I mean, and in some sense, this whole class will be essentially a demonstration of the powers of why the log function is useful. Because every one of these theorems will be such that we can actually show them for when we use the log function, but we wouldn't be able to show them for other functions. But let's start with this one. So we've got a distribution of n symbols with probabilities, and here's the entropy function of that distribution. Now, let's say that we've got any information measure. Let's call it this funny script h of p. So it's an information function, and let's say we wanted to have the following three, maybe natural and maybe desirable properties. The first one is that, well, if it's an information function, it should take its largest value when it's a uniform distribution. That kind of makes sense, right? When it's a certain distribution, it's low information. Uniform is the most amount of information on average. It's the greatest degree of uncertainty. Let's assume it has that property, number one. Number two, when we talk about conditional information, like how do we define h of x, script h of x given y? Well, h is really, and this is important to understand, h we're defining it as a probability, as a measure on a probability distribution, a single probability distribution. So now that we've got two random variables, well, how do we measure the joint? Well, we do it in this way. The conditional, whatever this guy does, and we're not saying what he does now, right? But we do know that there is this p of y given x. This is for fixed lowercase x. This is a distribution on y, and whatever that distribution p of y given x is, it's a vector of probabilities that sums to 1 for all values of y. We can stick it inside of h, right? Whatever that h is, we stick it inside of here, okay? And we can get a measure of information from that p of y given x, and then we can take the expected value of it with respect to x, to take the average of the conditional informations. And let's just define h of y given x in this particular way. Okay? And that happens to be property number 2. So let's say entropy is property number 2. And if we define it this way, then we have this notion of additivity. So that the information in a pair of random variables is equal to the information of the first one plus the residual information, because that seems to be an attractive property. That basically says if these are knowledge sources, x and y, if I know one of them, whatever I don't know about the second one is the residual, where this is the residual. Okay, that's property number 2. And lastly, property number 3 is impossible events don't change the information. So this basically says if we've got the information measured on a probability distribution of n events, which is this one, if we have another set of events which has exactly the same probability on the first one and exactly the same probability on the first n events and 0 probability on the n plus first event, that the overall uncertainty is the same. Okay. So those 3 properties. Does any of them seem reasonable? A better question is, do any of them seem unreasonable of what we might want in an information function for probability distributions? Would you say, oh, that one, I don't want that. I mean, does it make sense? If we send them there, oh, it's not just apples, oranges, and bananas we care about apples, oranges, bananas, and kiwis, but kiwis never happen in the universe, and so therefore, should kiwis, just knowing that they could potentially exist with 0 probability, should that increase our uncertainty? Let's do the fruit distribution. Should that? What about the first one? Does it make sense for the uniform distribution to the highest? kind of makes sense. What about the second one? That we define conditional entropy in this way, or put conditional information in this way, and we want additivity. That seems maybe reasonable, although that would probably be, maybe the most worrisome. Like maybe rather than taking the sum over x, we might want the max over x, or the min, or the median, or something else. Maybe this form of aggregation, even the average, is not what we would want. But on the other hand, the average is pretty good. We like probability. We take expected values. This has a nice interpretation of the mean. So it's like the mean information. But in any event, if we assume these things, it turns out, this theorem, this Kinship theorem, that any information function that has these three properties has the following form. Equation 2.3. In equation 2.3, it says that information function must be entropy according to some base. Lambda is a positive constant. So some base, so basically what it means is that whether we're using log base 2 or log base e or log base something else, that doesn't really matter. Because we did say it's it's the same up to a multiplicative constant. It just changes the units. So this is a reasonable justification for why log. And notice that log is in there. So square root doesn't work, polynomial functions don't work. That'd be log. So I'm not going to prove that theorem, but I think it's a really important theorem. Let's look at a couple of other justifications for logs in places that you may not expect. So let's play a yes-no guessing game. Okay. So we have a random variable x. Okay. And we have some set S, and S is a subset of the domain of X. So in other words, X is a set of the domain of X. By the way, this notation we haven't seen before. But this is the alphabet size of X. Like if it takes values from 1 through n, then domain of X would be equal to 1 to n. This is just a more general way of writing it, just whatever the domain is. And S is some subset. Like it might be all odd numbers, or it might be all even numbers, or it might be all prime numbers. It might be anything. And we can ask questions. Like we want to know what X is. X happens with some probability. And we can ask questions. And we want to try to figure out what the value of that random variable is as quickly as possible, asking the fewest number of questions. So here's an example. Let's say that x takes on 5 values. That's the domain of x. Let's say that these are the probabilities. So it's mostly probable to have value x1, and it's got 20% chance of having value x2, 20% chance of x3, and so on and so forth. Everybody with me? Now consider the following fixed guessing strategy. So I say, okay, I've got the distribution, I've got this. I get a random sample from this probability distribution. I want to ask questions to figure out what that value is. And all I get back is an oracle saying yes or no. When I ask a question, is it 3? Yes or no. Is it x3? Yes or no. Is it 5? Yes or no. Is it 5 or 3? Yes or no. And we want to, with certainty, figure out what that is. So the first question is x equal to a5. The next question is x is equal to x4. Then is it x equal to x3? And then is it equal to x2? And lastly, is it x1? So that's the strategy we do. The first thing we ask about is it equal to x5, x4, x3, x4, x1? So we ask 5 questions 30% of the time, right? Because 30% of the time the value is x1. And we don't find out that it's equal to x1 until we get to that value x1. And we ask 4 questions 20% of the time, because 20% of the time it's x2. And so the average number of questions is the dot product between the number of questions that we ask times the probability of that many questions being asked. 30% of the time we ask 5 questions. 20% of the time we ask 4 questions. 15% of the time we ask 1 question. Is that a good question asking strategy? No, it's not. I mean, on average, we're going to ask 3.35 questions. You might think, hey, that's pretty good. I'm asking only 3.35 questions from a 5-valued random variable. But can we do better? Maybe a better strategy is to first ask x1. We ask the question corresponding to the most probable event. So we ask one question 30% of the time, two questions 20% of the time, three questions 20% of the time, and so on and so forth. And just by changing which order we ask random variables, we actually get many fewer questions on average being asked, 2.65. So that's better. Is this the best? Is there a better strategy? So let's consider the following question strategy. So we write it as a tree. So the first question is, remember, we can ask any set. So we weren't fully utilizing our question asking ability with these singleton questions, because we were just asking whether it's a particular value, but the setting allows us to ask, is X a member of some set? Right. So the first set is x2, x3. So the first question we ask is X equal to either x2 or x3? And then we do different things depending on whether the answer is yes or no. So if it is X equal to x2 or 3, then we ask is it equal to x2, or we could equivalently ask if it's x3. And then we get x2 with probability 0.2, that's 2 questions, and x3 with probability 0.2, that's 2 questions. Okay? So that right away is 40% of the time we're asking only 2 questions. Then if the answer is no, that it's not x2, 3, then we have 1, 4, and 5 to deal with. So first we ask whether it's x1, and then if it's yes, then we say it's x1. So we ask 2 another 30% of the time. So that's 70% of the time we ask 2 questions. And if the answer is no, then we ask whether it's x4. And if it's yes, then it's if it's yes or no, we say either x4 or x5. So basically, 70% of the time we ask 2 questions, and 30% of the time we ask 3 questions. We never ask more than 3 questions, and most of the time we spend asking only 2 questions. The average number of questions asked is 2.3. That's much better than 2.65, right? So what does this have to do with entropy? The entropy is equal to 2.274. Or sorry, I can't read. 2.271. The one thing to note is that the entropy is smaller, but on the other hand, it's not that much smaller. What we're going to see is that the average number of questions asked can never be less than the entropy. So in some sense, what we're doing and what we've developed is, in this particular case, is a strategy for very probable events, or probable joint events, we ask few questions. And very improbable joint events, we ask a large number of questions. And when you think about what is the definition of entropy, it's the sum over x of p of x log of 1 over p of x. So p of x is the probability, and log of 1 over p of x is kind of like something that's related to how many questions we're asking. Now, log of 1 over p of x might not be an integer. But what if we were, when we're asking questions, we have to ask only an integer number of questions. We can't ask a fractional number of questions. So it turns out that one of the reasons why entropy is better is because the log of 1 over p of x might be fractional. But we must ask integral questions when we're actually asking questions. But it turns out that ends up not being an impediment if we do the following thing. If instead of asking questions about one random variable at a time, we ask questions about many random variables at a time. And if we ask questions about many random variables at a time, the number of questions per random variable asked, on average, can become fractional. And that's how we can ultimately then, on average, ask the entropy number of questions per random variable. That's called block coding. That's essentially what block coding is. And that's what we will be doing quite a lot of. But this is sort of our first instance of coding, right? We're just coding. You can sort of represent every outcome with a sequence of yes or no answers. We've developed a code for these numbers. Probable numbers, like x2 and x3, have
short codes, short sequences of yes, no. Notice that yes, no corresponds to binary, right? Longer ones, like the x4 and x5, have longer code words. So this represents a code. Now, let's look at the difference between the best first and worst first question. So the worst first question, it's like we're wasting a question. Like the first question we ask is always something we're going to pay. Right? When we're doing this particular thing, we can never ask fewer than one question. So we always ask. So we basically want to ask a question good questions as quickly as possible. And if we ask, is x equal to x5? That's like the worst first question you could possibly ask, because that x5 happens least frequently. Okay. And the opposite, you find out the least amount of information by asking the question, because it's the thing that you sort of split the thing into sort of two pieces, 0.15 and 0.85, and you get this entropy, which is it's the entropy of the split that you get, which is 0.5 and 0.85, and the entropy you get is 0.6. The best question, it turns out, is the one we asked in that tree, is x equal into the set, x2 and x3. So the probability that it's yes is 0.4, the probability that it's no is 0.6, and the entropy of that question, if you think about the entropy of the question as the entropy of that binary distribution that you get by splitting the probabilities and adding them up, the entropy of that is entropy of 0.4 and 0.6, which is 0.971. And 0.971 is much bigger than 0.6098. So in some sense, the entropy is going to be the thing that measures how much information you're getting on average about what random variable it is. And what this seems to suggest is that you want to ask questions early that have high entropy. This might even make you think of an algorithm, like a greedy algorithm, where you ask first the question that has the highest entropy, and you ask next the question, depending on each outcome, you ask next the question that has the highest residual entropy. You keep doing that until you know the answer for certain. That actually is a good strategy. It's not optimal, but as we will see. But the basic intuitive idea I want to impart to you right now is that it's better to ask questions first that have high entropy, because this quickly reduces the remaining uncertainty. Now, I think I have the slide that explains what we mean by that. So in some sense, there's the entropy of that distribution, which is the information in that distribution. When we ask a question that has high entropy, we subtract off that entropy from the entropy of the distribution, and the uncertainty left over turns out to be this subtraction. So it's exactly analogous to this relationship, like the entropy of x and y, where x and y are two random variables. You have the first random variable, which is that random variable over 5 possible values. The second, like x would be the x. The second random variable is y, which would be the clustering between the yes or no questions. Like, is it x5 or is it not x5? Or is it x2, x3, or is it not x2 or 3? That could be the random variable y. It's just a binary outcome as the outcome of that question. And we said these things can be correlated. And so if we ask, let's say x is the first question, it's the yes no question. So this entropy, x, y, is equal to the first entropy, which is the entropy of the first question, plus the remaining uncertainty about what we don't know about. Given x, what's left over in y. And so if we ask a first question that has the highest entropy, high entropy first, there's going to be a little remaining uncertainty left over because of this additive property. So therefore, we want to ask first the questions that have high entropy in general. Like I said, that's not a design strategy. Let me write down, in case this isn't clear, how this sort of works. So we might say that, let's say that x is equal to it's a 0-1 random variable. 0 corresponds to, this is not good. I'm trying to invent notation at the same time. Hold on. Basically, what I'm trying to say is that x corresponds to the first question we might ask. and y is the remaining uncertainties, which is what's left over. And so if we ask quickly, if we ask early on questions that have high entropy, we have the remaining. I was going to do this whole example, but maybe I shouldn't do that on the fly, so I'll just make it messy. Okay, so any questions about this? Because this is a really important point. Let me do it demand-driven. Everybody clear on this? Okay. So next we're going to define, by the way, so that also sort of answers the question as to why log. So the log function measures in, a real unit, which is like number of yes/no questions, how much information we're getting from a set of questions, and also like how a description length. Where description length is measured in terms of yes/no symbols, or it turns out in bits. And since we care about communications and we care about computation and everything's encoded as bits, log base 2 is sort of a very natural base. And log is a very natural, because it corresponds to things like description length. And description length is exactly what encoding is. I mean, when you compress a source, you represent it with a description that's not the original source. And you want the average description length of your source to be as small as possible. And so the kinds of questions we're going to ask is, what's the limit? What's the limit of compressibility? What's the smallest we can compress? And we're going to see that the entropy with the log function, the entropy is the limit of compression. We can't compress it any smaller than the entropy. It's funny, it used to be the case that there would be companies every once in a while that would pop up and claim that they've invented a compression algorithm that compressed down to below the entropy. And it's getting back again to what we said last time, which is that like if you run gzip on your text file, everybody know what gzip is? If you run a compression or a zip file, you must know what a zip file is. Everybody know what a zip file is? This means yes, this means I'm not sure, and this means I really don't know. If you zip a file and then you zip the zip file and you zip the zip file, does it get smaller? No, because you've compressed it down to its entropy limit. And once you've done that, you can't get it any smaller. There's sort of a fundamental amount of information in any source, and that information corresponds to its minimal description length, which corresponds to the entropy, and which corresponds to the smallest amount that you can compress something into, smallest number of bits that you can compress something into. That's the information. If you want to see how much, if you write a report for your English class, and you want to see how much content is there, compress it. That's a great way of grading something. Compress a paper, and those that don't compress well get an A. Those that compress well get an F. Okay, let's talk about mutual information. That's also a critical quantity that we're going to be using. The question is, how much information do two random variables have about each other? Like if I know x, like this x and y may or may not be independent. Let's just say we don't know, but if we know x, it might help us learn something about y on average. And if we know y, it might help us learn something about x on average. Is there essentially a way of measuring it? If we do know that the random variables are independent, then if we know x, that shouldn't tell us anything about y, and vice versa. Independent random variables don't help each other. So that quantity, I mean, where information is measured in terms of entropy, that quantity in our context is going to be called the mutual information. So let's first of all talk about the event of mutual information. So we can ask for the information provided about an x from the fact that y occurred. And so this is going to be I of x semicolon y. You can write it in a number of different ways. It's the ratio of the conditional to the marginal. The log ratio of log odds is like the log of the probability of x given y times the probability of x. We can also write it as this difference. It's like the information in x minus the information in x given y. So you can think of it as like the surprise. The first term is the surprise that x occurred. This is the first term here. It's not clear. And the second term is the surprise that x occurred given that y occurred. Right? It's the difference in surprise for that particular event. Like maybe X is really improbable. It's really surprising. But then once we find out why, X suddenly becomes very probable. So it's a reduction. On the other hand, you might be more surprised. Maybe X is extremely probable, marginally, but as soon as we know why, X becomes impossible. So the way you think about this is a difference in surprise. Another thing to remember is that the probability of X given X is always going to be equal to 1. Now why is that the case? It's basically saying, given that X occurred, what's the probability that X occurred? Well, it's 1. It has to be 1. So that means that if you look at, for example, like the information between X and X, it's log of 1 over P of X minus log of 1, which is 1 over P of X. So I of X can be seen as a form of self-information. Like the information that you learn about X given that X occurred. How much does X tell you about itself? It's equal to the original information function. And we said a little bit earlier today that we're going to encounter the word self-information. So entropy, if you take the average entropy is sort of like the average self-information. Now the mutual information is not the self-information, it's like the co-information between two random variables. And it's defined in the following way. It's the average over the joint distribution X and Y. So let's look at all of these guys carefully. So we average over the joint distribution X and Y of this log odds thing. Okay. Another way we can look at it is the average over the joint information of this quantity here. And here what we're doing is we're just multiplying numerator and denominator by P of Y, which is 1. But we can do that because then we can turn it into this quantity. It's the joint, remember, P of X given Y times P of Y is equal to P of XY. It's the chain rule of probability. So the numerator then becomes, this is the numerator here, and the denominator becomes the product. So it's kind of like, you can think of it as the expected value of the log odds between the case when the two random variables are, the probability of the two events are considered together, P of X comma Y, and the product of the marginals when they're considered separate. When the random variables are truly independent, then P of X comma Y is equal to P of X times P of Y, and the numerator and the denominator in this guy are the same. Right? So that, of course, means that the mutual information, just right away you can see the mutual information will be 0 in that case, because it's like log of 1, and it's the sum of a bunch of logs of 1s. So another way we can write it is, I think that's the same way. Yeah. Oh yeah, sorry, this is just the sum form. This is what it is. Mutual information is defined as the sum over all xy of the weighted log odds between the joint and the product of the marginals. Now, we have a number of properties right away. The mutual information is equal to the reduction in entropy, is equal to the entropy of X minus the entropy of X given Y. So how much uncertainty is there about X minus how much uncertainty is there about X given Y? So it's just sort of saying how much information X and Y has about each other is sort of the degree to which Y reduces the entropy. It's like the entropy reduction. You think it's like a gain, if you will. Gain of X in context of Y. Actually, that's not correct. It's like it's the marginal minus the gain. That's probably not even a useful term to use in this context. But in any event, the point is that it's a reduction in entropy. And the way we can prove it is just by looking at the definition of mutual information right here. And that's just using the properties of the log, and then that just gets us the entropy. And by symmetry, it's equal to h of y minus h of y given x. So it doesn't matter which one we subtract from which. It's either h of x minus h of y, x given y, or h of y minus h of y given x. Same value, guaranteed. Thanks again to the different way we can represent a probability. P of x y is equal to P of x given y times P of y. It's also equal to P of y given x times p of x. Right. I hope I got that right. I think I did. Did I get that right? Yeah. So now we know that the entropy is non-negative. We also know that the conditional entropy is non-negative. Why is the conditional entropy non-negative? Again? Because we are averaging a bunch of non-negative values. And the weighting coefficients of the average are the probability, and so therefore it's going to be non-negative. So both of these guys are non-negative, and so therefore the mutual information is bounded by the minimum of the corresponding entropies. You can never learn about something more than there is to learn. Right? You can never learn. I can never teach you more than there is to know. If I could, I would be definitely a highly rated instructor. Right? Actually, I wouldn't exist, would I? So the point is, getting back to this sort of quantifies that. Because information, when we talk about information, we talk about learning, we talk about communication. You can't communicate more than there is to send. Right? And we're going to quantify that. We're going to actually have a lot of that. So that's this discussed intuition. Have we sufficiently discussed this intuition? You guys are very quiet, and I don't know how to interpret being quiet. So being quiet could mean that my lectures are extraordinarily clear and everybody understands everything, or it could mean that everyone's completely confused, or it could mean that you all just happen to be really quiet people. But remember what we said last time was that the only bad question is the question that goes unasked. And the other thing we said last time, I think, we said this was smart people ask a lot of questions. Right, that's not to imply anything. And it's that you're not a lot of questions, but it's a general property when very smart people always ask lots of questions. So if you want to be perceived as being smart, just ask a lot of questions, even if you're not. No, I'm just joking. You're, of course, all very smart. But I want to open it up for questions. I want to. The point of this soliloquy is really to sort of encourage you to ask questions. And I'm just gonna say all this nonsense until somebody asks a question. Unless you really don't have a question. Raise your hand if you really don't have a question. So, what's your question?
Like the one given x is the amount of information by giving x. I'm confusing about the user information and the conditional.
Okay, so remember, zoom in on this guy. This is the amount of information in the random variable y. This is the average amount of information in y conditioned on all of the events x is equal to lowercase x. And what this is saying is that the mutual information is sort of the entropy reduction. So here's maybe a plot. So the idea is that, let's see, I think I can add a page here. Okay. So let's say we've got so this is sort of information, I, or some sort of entropy. So let's say that this value is the entropy of x. Right? This value here is the entropy of x when we know y. Right? It's reduced. And this value this is how much the entropy is reduced. This is the mutual information. It's the reduction in entropy. H of x minus h of x squared y. And it turns out that that value, this quantity, just so happens to be equal to exactly the same value if we were to say measure
h of y, and this is h of y given x. Notice that these values are the same. The interval lengths are the same. That doesn't mean that h of y is equal to h of x. It doesn't mean that h of y given x is equal to h of x given y. It just means that interval, that space. This interval and this interval are the same. That's all it means. Okay, does that answer your question? Okay. So, right. So let's talk a little bit about mutual information and entropy more. So remember the chain rule of entropy, h of x, y. That we said is equal to the information in x plus the residual entropy in y given x. That's different than the mutual information. The joint information in x and y is not the mutual information between x and y. However, there is a relationship. The mutual information is equal to h of x minus h of x given y. Don't get confused with commas and semicolons, right? So first of all, entropy, this is a great way of getting points taken off from your problem sets. By the way, this is the person who will be taking off your points. So that's a great way of meeting someone. Hi, I'm the person who's going to be taking off points from your problem sets. Nice to meet you. The entropy uses commas between separate random variables. Let's see if we can zoom in on the comma. We can't zoom any more than this, but comma, right? The mutual information uses a semicolon and an I. Conditional entropy uses a vertical bar and an H. Entropy uses an H. So if it's H and commas, it's joint entropy. If it's H and vertical bars, it's conditional entropy. If it's I and semicolon, it uses, it means mutual information. It used to be the case that people used H for everything, and the only difference was a comma and a semicolon. And that got really confusing, because sometimes there'd be papers and the upper dot of the semicolon just didn't print. And wait a second, is that entropy or mutual information? Then they started using I and commas. That was also confusing. So now they use I, it's like it's redundant, right? It's an encoding of information about information theory. And use I's and commas, semicolons. So now that we've got the comma semicolon thing disambiguated, what we can do is combine this guy and this guy together to get an expression for the mutual information in terms of just the entropy. So it's just the entropy of x plus the entropy of y minus the entropy of the joint. Now this is sort of, as some of you might be aware, this is actually a very first instance of maybe what's known sometimes as the inclusion-exclusion principle in combinatorics and enumerative combinatorics. We are including x, we're including y, and we're excluding the joint. And it goes on. But sometimes we can visualize these things with pictures. Okay, so let's visualize them. Because we can actually use Venn-like or block-like diagrams. So here's sort of a measure of the information in X. So this is useful, but it also can potentially lead to confusion. So you know how you can actually use Venn diagrams for probabilistic events, and you learn these in your probability class. Like here's this event, and here's this event, and so on and so forth. Here, what the area here is sort of meant to represent an amount of information and what information it is, right? Because it's a property of a probability distribution, not just a particular event. So it's the entropy of cap x. Okay, so more uncertainty would be more area, higher entropy would be more area, less entropy would be lower area. So the other thing to note is that they're not really sets. I mean, this is the area of the regions are meant to convey degree of information. And we're soon going to see overlap sets. Overlapped regions correspond to overlap of information. Like the intersection consists of information that's on average real by both x and y, but it doesn't necessarily mean that there's actually a set of items or something. We're just sort of using sets and Venn-like diagrams. We will be doing that just to convey degree of information. So then we can get this relationship between
entropy and mutual information, conditional entropy. So we have an entropy of X, which is the blue circle on the left, including the sort of gray part. The entropy of Y is the yellow oval. These are ovals or ellipsoids or something. So the entropy of Y is equal to the yellow plus the gray. The conditional entropy is X given Y. So given that we know Y, all this stuff here, I should just write here, all this stuff here is known, and it's the residual stuff, which is this. If we know Y, the residual is the blue, it's the dark blue. Okay. Symmetrically, if we know X, then this becomes known, all this stuff becomes known, and the residual information is the yellow. The common information between both is the mutual information. This is the common, this is that which overlaps. The joint information is all of this stuff. Right? We don't count the overlap twice. If they were independent random variables, the Venn diagrams would look like this. There'd be no overlap. But because there is a dependence, there's an overlap. Right? Okay, any questions about this? Okay, so you can sometimes use these kinds of pictures to prove theorems, as you'll see, but it's a little bit tricky. So this is really meant more for sort of intuitive understanding. Don't try to, say, prove a theorem by using these kinds of pictures. We will see some more elaborate versions of these pictures. But again, I want to stress right at the beginning, when you first seen them, that they're meant to convey intuition, not so much to prove a theorem. Okay, let's talk now about the Kullback-Leibler divergence, the KL divergence. This is really a way of measuring in information theoretic terms a value that corresponds to the degree to which two probability distributions over the same alphabet size are different or not, or different or similar. So we have two distributions, P and Q, and the Kullback-Leibler divergence between these two distributions, as we will see, has some very, very important and fundamental relationships to information, to entropy and mutual information. So the question is, like, how do we define a distance? Now, I put distance in quotes because distance actually has a precise mathematical meaning. So it's not really correct to call it a distance, because a distance would imply that it satisfies something like the triangle inequality. We're not saying necessarily that it satisfies the triangle inequality. So in general, we're saying it's a divergence. So a divergence is still going to be non-negative, but it's not necessarily going to satisfy triangle inequality. So one way of constructing a distance-like thing, maybe I should clarify this and change this wording just in case it's confusing. It's a distance-like thing. This is actually, believe it or not, very important. I've had papers rejected from reviewers because we accidentally called something distance occasionally, then divergence. So don't make the mistake I did. When you mean distance, use distance. When you mean divergence, use divergence. Okay? These have precise meanings. So here's an example of a possible distance-like thing. We can just take the sort of Euclidean, the squared Euclidean norm between the two probability distributions. But we would sort of like sort of an information distance. Like if we think of one distribution as Q, but it really is P, like what do we pay? What sort of penalty do we pay in terms of, like, say, like for example, suppose in this question answering thing, we design this strategy for the optimal number of questions in order to figure out the outcome of a random variable, but we do this with respect to the wrong random variable. So, sorry, the wrong probability distribution. How many extra questions on average might we ask? If it's optimal with respect to the wrong distribution, it stands to reason that maybe there'd be some sort of divergence that would say, okay, well, if you're optimal if it's optimal with respect to the wrong distribution, the number of extra questions you ask should be some function of the two distributions alone. And that's, it turns out, what the KL divergence will give us. There was a question?
So does it have any meaning if the top bets aren't actually the same? Because you say they have to be the same number. Would there be any reason to measure the divergence between the two colors?
Yeah, no, I know what you're asking. I mean, so what you could do is, for example, have the smaller one be padded with zeros. I mean, if there's really no correspondence, then it doesn't make sense. Right? I mean, there has to be a correspondence on at least the ones that have common overlap. If one of them is smaller than the other, you could pad it with zeros. But in general, we should best think of it as the same underlying alphabet. So anyway, you might think of this. This is sort of more of like a compression inefficiency. So the Kovac-Leibler divergence is going to do this. It's also called the information divergence, or sometimes it's called the information for discrimination. Those are older terms, but you still occasionally see them. You should be familiar with these terms. This one, of course, this one. And remember, it's really called the Kovac-Leibler divergence more so than the distance, because it's not a distance. So you should really, if you want to be technically correct, call it the Kovac-Leibler divergence. Now, given two distributions, okay, so how do we define it? Here's how we define it, and I'm running out of time. Let's just quickly go over the definition, and we'll end with this. I'm going to write end. So what is this? Basically, it's first of all, note that it's the sum over x, so it's not a symmetric thing. Distances have to be symmetric. This is not symmetric. So d of pq. So p, the position whether we put p here and q there matters. So if you switch p and q, you get a different thing. You're summing over x, probability of x times the log odds of p versus q. So it's a little bit like entropy. If you just think of sum of p log p, it's like the negative entropy minus something else, right? And which we turn into the cross entropy. But it's entropy-like, entropic-like. And it turns out that this will be our coding penalty length for using the wrong distribution, as we will see. But we're not going to have time. We've got to end. So are there any last-minute questions? Any second to last minute questions? Okay, don't forget about homework 0 due tonight. Our TA should start grading them, like maybe even you've already graded some of them, hopefully. I'm saying this on record, by the way. Yeah, so you've already started grading. So it should be the case, I think, that after he's graded them, you'll see the comments right away. By the way, this is, like I said, it's not graded, it's just a credit or not credit, but you're still going to get some feedback from our TA. So as soon as each one is graded, you're going to get the feedback. So some of you might, it might be the case that he does some of them on Tuesday and some of them on Friday. So if some of you get grades back and others don't panic or anything. We haven't forgotten about you. Okay, I will see you on Thursday.